Hi, welcome to the third and final part of our periodicity free response practice. This is Mrs. Dalberg, and let's go ahead and get started with the year 2000, number 7. And we have a question about selenium compared to bromine, and we want to know why the first ionization energy is less than that of bromine. And so if we look for those two guys on the periodic table, we see here's bromine and selenium. And we see they're in the same energy level. The only difference is that bromine has one more proton there. And so, kind of move this back out of the way. Let's look at a good explanation for why bromine would have a higher ionization energy, or it would take more energy to remove that electron from its outer shell. And so if we look at the answer to that, it says the electrons in both of them are in the same energy level, but bromine has more protons and the attraction to the nucleus is greater. And so a good answer should talk about the fact that they are in the same energy level and those electrons are coming from the same orbital even, the p orbitals. And bromine just has more protons. That's the only reason why, that greater nuclear charge. Okay, the next question is, why is the ionization energy of selenium greater than tellurium? Okay, and so if we look at our periodic table, we will see those two guys, selenium versus tellurium, right here. And now we have different energy levels. So if you notice that theme, um, this guy, his electrons are much easier to remove than selenium. Selenium is in that 4th energy level, tellurium's in the 5th. So that outer electron is further away. It's shielded by all these other energy levels. And so if we move this out the way, let's look at a good explanation for that. So the electron removed from tellurium is in a 5p orbital, while the electron removed from selenium is a 4p orbital. The 5p is at a higher energy level, and the removal requires less energy. You should probably talk about the fact that even though tellurium has more protons, the fact that that electron is in a higher energy level makes it easier to remove. Always address both charge and distance from the nucleus. Okay, 2006, number 8. Okay, now it says use the periodic table, and we're going to predict something about Q. It says we have a new element Q. It's been discovered and has atomic number 119. And we want to write the ground state electron configuration showing only the valence shell electrons. So with that being said, we probably need to look at the periodic table and figure out where would element 119 be. And so if we go down here, we see the highest number on our periodic table is 118. If we found the next element, it would be found right here under francium. And Q would be right there, and it would be 119. And so knowing that, let's look at those questions over here, and let's answer those. So if we know that that element would be right here, what would be the electron configuration for the valence electrons? So we might want to count the energy levels. So if I pull this out, we have 1, 2, 3, 4, 5, 6, 7, Okay, that would be 8s1 for element Q, right down there. Okay, would it be a metal or a nonmetal? And explain in terms of electron configuration. Well, if it has one valence electron, it's got to be one of those alkali metals, right? Um, so that valence electrons would be easily removed, and so all of those properties would make it a metal, not a nonmetal. Okay, on the basis of periodic trends, it would have the largest atomic radius in its group, or would it have the smallest? Well, we know as you add energy levels, the size increases, so it would definitely have the largest because it has the most number of electron shells. What would be the most likely charge? Well, if it has one valence electron and it easily loses that one valence electron, the most likely charge would be +1. So Q +1 would be our most likely ion. So if it react with a carbonate ion, what would the chemical formula be? The chemical formula would be Q2CO3. Just kind of like potassium, except it's Q. That's how we'd write the chemical formula for potassium carbonate. We just have a different element with a +1 charge. Would it be soluble in water? And explain your reasoning. Well, looking at, the only way to know this is our fictitious element, is to look at the other properties of everything else in the family. And if we look at the other metals up here, we know that these are the little babies. These guys are always soluble. So Q, if it were undiscovered, would probably be soluble too. Okay. Moving on to 2006, number 7. Account for each of the following in terms of atomic theory and/or quantum theory. So atomic size decreases from sodium to chlorine in the periodic table. So how do we account for the fact that, and let me go back here, and I'm just going to grab this, and we'll look at this. So we're looking at sodium to chlorine. So account for the fact that it decreases in size. And so if we look at that, the two things you want to address are charge, what happens to the charge as you go across that period, and size. So if we look at charge, we know that as you go across, you increase the number of protons. So the charge increases, but the size, what would happen to the size? As the number of shells increase, the size increases, but we don't have more shells. We're in the same shell. So for this one, if you talked about the number of protons in the nucleus increase, the added electrons result in an increased nuclear charge. Therefore, a greater attraction for the electrons, pulling them closer to the nucleus and making the atom smaller. Okay. I would probably also add in there that they're in the same shell. Okay, the next step, the first ionization energy of potassium is less than that of sodium. And so let's look at potassium compared to sodium. Those two are right here in group 1. And if we look at that, it takes more energy to remove an electron, a valence electron from sodium than potassium. Potassium is easier to remove. So why? Let's look at the answer. It says both of them have a 1 valence electron, but K's valence electron has a higher quantum number, or it's further from the nucleus. It's in, it's one more shell away from the nucleus. That greater distance results in less attraction. Even though, if we look at potassium, it has more protons than sodium. Sodium only has 11, potassium has 9. You would expect it to be smaller, but it's the fact that it has an extra quantum level or shell. So for this one, we have 1 point for the size explanation, 1 point describing the attraction to the nucleus. For the previous one, you got 1 point for attributing the size decrease to the attraction of the nucleus by the increase in nuclear charge. Okay, now we're in 2007, number 2. We're talking about percent abundance of an isotope. And then we're going to keep going and calculate the energy to break a bond. And so if we look at this, we're given an isotope, 2 isotopes of neon and their masses, and we're given the average atomic mass from the periodic table, and we want to know the percent abundance of each isotope. And we know that if we add these 2 guys together, they'll equal 100%. So we would just want to know, when you break this down, what percent of each is available. So if we look at this, we're going to let X represent the abundance of neon 20. So this is represented by X. Now, we don't want this to be another variable, so we're going to let neon 22 be 100% minus X, or 1 minus X. And so if you have these 2, it's kind of like taking the average. If you have 19.99 times X plus the abundance of this, or this isotope, times the abundance of either 100 minus X or 1 minus X, and all of that equals the average atomic mass, then it's just simple algebra. The hard part is probably setting up this relationship. And so if we keep on going, kind of go through and let you look at how they reach the answer to this. When you solve for X, you get 0.905. And so X is the percentage of this first isotope. So if you multiply that by 100, you have 90.5%, and the rest of it must be the neon. Okay, part 2 of that says if you have, if you want to know the number of neon 22 atoms in a 12.55 gram sample of neon that's occurring. And so what we want to do is, we know that the average atomic mass of everything is 20.18. But for neon 22, we just calculated that only 9.5% is neon 22. So if we can take our original sample and figure out how many atoms, and then we could take the total number of atoms and figure out what percent of that is 9.5%. Then we know how many neon 22 atoms we have. So the first step is to figure out the whole, and then we can figure out the part, because if we know the percentage, we know that always equals the part over the whole times 100. So coming on down here, we'll look at the solution to this. We had, the first step was to find the number of atoms, essentially. So if we have 12.55 grams and we get to the moles of neon, and then from the moles of neon, we want to figure out how many atoms we have. So we could do that next if we wanted. And this step is in every 1 mole, only 9.5% is neon 22. So this is kind of all done in one step. And if you look at the answer, that is 3.6 times 10 to the 22 neon atoms. If I worked this, I would probably have done this step after. I would have found the number of atoms total, and then I would have multiplied that by 9.5%. So this one was actually worth quite a few points. And my computer is freezing, so I'm going to stop and I will continue.